Okay, so thank you for the introduction. Today I'm going to try to give you all some hopefully new insights on the design, the implementation, and the programming practice of Julia from a programming language perspective. So I'm not driven by any particular end application. Of course, I won't have time to cover all of it, so if you want more details, you can find them at an article that was conditionally accepted to UPSLA and whose co-authors are here. All right, so engineering Julia for speed. Let's begin by, well, checking the implicit assertion of this title. Julia is indeed a fast programming language. What you can see here is the slowdown of compared to C of Julia in red, JavaScript in blue, and Python in green on a variety of benchmarks from the programming language benchmark game. So those benchmarks are quite small. They're not here to nail the issue of what programming language is the fastest, but they still give some insight. And the results are that Julia consistently outperforms both JavaScript and Python and is within 2 times of C for most of the benchmarks. There are some exceptions, for instance, Mandelbrot, on which the C loops are manually optimized and this cannot be reproduced at a higher level, but still, Julia is fast. Now the trouble is that Julia should not be fast. Julia should be terribly slow. And the reason for that is that, well, first, the surface language is not typed. And you can actually write fully untyped code, which should be very stressful for the compiler. Second thing, there is an eval, like in JavaScript, so that allows you to load arbitrary pieces of code into runtime, and that's terrible to optimize. Third, there are some reflection capabilities, like in Python, and reflection allows you to display something that are supposed to be done at compile time than to runtime, so it's also difficult to optimize. So the question is, how come Julia is so fast and both so expressive in a way? I believe the reason for that is a combination of 3 things. First, the design of the language that avoid making things that are unoptimizable. Second, the implementation that leverages a number of choices from this design. And third, programming practice, because it is possible to write terrible code in Julia, but it is also possible to not do so, and you have to follow a few simple rules. Let's begin with the design. So, I won't have time, again, to cover all of the design of Julia. Obviously, I'm not the documentation. So I'm just going to focus on 3 points. First, dynamism. Julia is a dynamic language, but this dynamism is in balance. For instance, I just talked about eval, but eval is restricted to the global scope. That's very different from JavaScript, because it means that you can't tinker with the internals of methods from which you're actually calling eval, which makes the optimization unnecessary in a number of cases. Macros allow for much dynamism because they extend the syntax, and they're syntactic macros, so they manipulate the tree, and they're not C-like macros. But at the same time, they do not interfere with optimizations because macro expansion happens way before all those optimizations. And a third thing which is introduced by, for instance, eval, is that you can replace methods at runtime. And replacing methods is a very tricky thing to implement in the compiler. And in Julia, there is a world age mechanism that allows you to replace methods in a very clever way, because you have a timestamp that says for how long a method can live. And if you want to replace it, you will just cut the upper bound for the old method and create a new one. So this is for dynamism. Then there is a second point of design which is crucial in Julia, which is the type system. It is very rich. User can define abstract types that cannot be instantiated, and concrete types. Among the concrete types, there are primitive types, which are sequences of plain bits, and composite types, which are C-like structs, and for which the fields can be annotated with other types. There are union types, tuple types. You can have parameters, and those parameters can be bounded. 3 more detailed points. First, all type annotations are optional in Julia, and I believe that this is somewhat representative of a more general philosophy of Julia, which is that if you want to write the simplest code that you can write, you can do that and just let the compiler do all the work. That's fine. But if you want to give more information, you can also do that. Second thing, concrete types cannot have subtypes. This is very important for a number of optimizations, and among which unboxing, for which I'll come back later. This means that the concrete types are like Java's final types. And finally, all types are parametric, and this allows for, well, to extend the syntax of types a lot, because you can you can parameterize all your types with bounds that can be bounded with other types, etc. Now that we can have types, we can go to multiple dispatch. So I'm pretty sure that everyone here knows what multiple dispatch is. Simply when you have a call, you will select among the applicable methods. So those methods are those that have a type signature, which is a supertype of the call signature. You will select the most specific one. So in that case, it will be the float and float method. I just want to mention one thing. Multiple dispatch occurs at each call. This is a semantic remark, because multiple dispatch is part of the design of the language. Of course, in a number of cases, it's not necessary to incur the cost of multiple dispatch. So for instance, if you only have one method for a function, obviously we'll dispatch this unique method. But it doesn't mean that dispatch does not happen. Right. So now that this is covered, let's try to see how the implementation leverages those choices to make Julia code efficient. So I've heard a few days ago that some people said that Julia was just ahead of time compiler. Let's try to see what this means. Here's the compilation pipeline of Julia. So when you're just executing a Julia file or including one, it all begins with source code. Source code is parsed and then macro expanded. And this is all done from an AST, which is a Julia object of type exp. Then this expression is lowered to an internal representation. And as you can see, you can access the different stages of the internals of the compilation using macros such as code lowered or at macro expand. Once code has been loaded into memory, runtime can begin. And runtime consists in a very simple loop. You have a function call. This function is dispatched. And then you get a method, which is executed, and which will probably call other functions, etc., etc. Now, the interesting part is what happens during dispatch. The implementation of Julia specializes the method you have dispatched on according to the concrete types of all of the arguments. So when you're dispatching, you have a concrete call. Either you already have in memory the specialized method for this particular call signature, in which case you simply execute it. Otherwise, you begin a specialization cycle. Specialization takes the internal representation that was loaded in memory of the method it was dispatched on, and begins with type inference, which is a data flow analysis that propagates the types, so the concrete types, from the signature through the body of the function. What can happen during this stage is that maybe you have another call within this method you're compiling, and if type inference is good enough in your case, you may be able to infer the concrete types of all of the arguments to this new call. In that case, you already know at compile time what method this particular call will be dispatched on. And as a consequence, you can already launch another specialization cycle for this subcall. Right, so this is the reason for the back arrow here. Once code has been typed, it undergoes a series of transformations, starting with SSA conversion, and then a number of optimizations. Finally, sorry, yeah? SSA is static single assignment. So it is a form of the internal representation where each variable is only assigned once. So this was introduced by Keno's new optimizer, so it's pretty recent. And finally, after code is optimized, it is translated to LLVM that generates native code. Once we have native code, it is stored in memory in the method table of the function, so that next time the same function call, the function call with the same call signature happens, it can be directly, this specialized method can be directly called, and of course it is executed. Right, so just to recap, I think there are three main stages in this compilation cycle. The top line represents roughly the front end that deals with source code. The second line, and a bit more, represents the middle end, which is how Julia internally transforms all this code. And finally, the end of the third line is the back end, so LLVM that generates native code. Let's focus a bit more into detail of the middle end. So as I said, specialization begins with type inference. Let's see how this works in practice on an example. I have one method here, and I'm going to specialize it for one argument of type int. Type inference propagates this type through the body of the function. So for the moment, through all those first operations, there has been no modification to n, so the type of n is always int. Then we're dividing n by 2. This yields a float. Arrived at the end of the loop, we have to unify the type of the end of the loop with the type at the beginning of it. So n at the beginning of the loop becomes a union of int and float. We can propagate that again. And once we arrived at the end of the loop, either an int or a float divided by 2 always yields a float. Right. So now question, what is the type of n just out of the loop? Any idea?
What was the question?
What is the type of n just outside of the loop?
It's the same. Just outside.
It will be the union of an int and a float, because it is also possible that we never enter the loop. Right? So, type inference can be quite tricky, and this is not the tricky part. The tricky part consists in recursion and all the parts. And what actually happens during type inference is that all the variables are inferred at the same time. So here I haven't shown it, but there is also type inference for variable r, which is always inferred to int in that case. So in the end, we know that the return type of this specialized method will be int. That's good, because we know the concrete return time of the function, of the specialized method, sorry. And as a consequence, we're saying that this method is type stable. Now, this method is type stable, right? But there is an internal variable, n, which is not type stable, because in that case, there is at least one point in the method for which the concrete type of n could not be inferred. For instance, just before the division, we didn't know if n was an int or a float. And as a consequence, we don't know what method will be called for the division. There is, in this case, a very simple way to remedy that. At the very beginning, we can put a conversion to float. And in that case, we know that n is always a float through the body of the specialized method, and r is still an int. Now, why is type stability important? Type stability is crucial in order to perform devirtualization. So, devirtualization, which is often confounded with inlining, consists in displacing the cost of multiple dispatch from runtime to compile time. In that case, for instance, if I'm taking the line with the division, n divided by 2, since we know at compile time that n is a float and 2 is an int, we know what method will be called, and so we can already dispatch at compile time. So devirtualization consists in replacing the generic dispatch operation, which is quite costly, into a direct invocation of the specialized method. Devirtualization allows inlining. So here is an example showing the two. Let's take a function foo that just returns 42 times its argument, and two wrappers around that function. The first, with type, simply applies foo to y, which is an alias of x. That's the left part. On the right part, there is another wrapper, no type, that also applies foo to y, and y is remove type of x. So remove type, I'm not showing it here, is just the identity function, but with internals so fuzzy that type inference cannot go through it. And as a consequence, y cannot be inferred to be an int. It's, the type of x. It's just any. And we can see that by calling at code typed before optimizations on the two wrappers. On the left part, y has correctly been inferred to be an int, so I'm calling that with type of 3, so 3 is an int. And as a consequence, we know that foo of y will be a call to the specialized method for foo with int as an argument, and we can type in for foo very easily, it yields an int, so we know that the return type of this will be int. On the right part, however, since we don't know the type of y, we can't know what method for foo will be called, although there is still one, but that doesn't matter here, and that, as a consequence, we don't know the return type. Now, after optimization, inlining happens. So on the left part, what's good is that we know what method is called, so we can replace the call by directly the body of the function. So we replaced foo of y, by 42 times y. And y was also replaced by x, and the times was also replaced by this internal function molint. On the right part, there's something very interesting that's happening. So just coming back there, remember that there is the first call to remove type of x. The type of x is known. So the call to remove type can be devirtualized. It can even be inlined. However, inlining and optimizations have to happen after type inference. And as a consequence, even though the call has been inlined, there is an implicit line here which is y equal x and equal to foo of y, and foo of y is thus replaced by foo of x. But the type of x has been lost. So, as I just explained, foo cannot be devirtualized in this case. And that's very bad, because if you see the native code generated by this, on the left part, there is only one assembly operation, the basic multiplication, and the right part, I'm not even showing all of it. It begins with a lot of allocation, stack operations. There is a boxing, because you have to box the integer into an any box that can be let down to C in order to operate dispatch, etc., etc. So that's all very costly operations. Another optimization I want to mention is unboxing, because it's quite specific to Julia. So here is the representation of a generic array in Julia. It is a sequence of pointers that point to boxes composed of a pair of value and a type. So if you want to add a value to this, that's simple. You just add a box with the value and its type. Right. The thing is that this representation is not very sparse, and there is a lot of repetition in the case where all the types are the same. So unboxing consists in saying, if I can write that, I can also write that. I'm just putting the type as a parameter of the vector, and I'm storing all the values inline. This is much better, because it means that you don't have to dereference anything while operating and iterating over the array. And that makes things way faster. It's also much condensed. Actually, the unboxing is more general than that. You can also operate that on structs. So for instance here, this is the representation of a generic struct with fields that have not been typed with concrete types. So so in that case, it's a number and any for the types of the fields. And you have boxes. But if your types are concrete and actually are bits filled, in that case, you can also store them in an unboxed fashion. So why is unboxing interesting? Well, I think that explains in great part why it is said that iterative code is faster than vectorized code in Julia. So there is nothing wrong with vectorized code in Julia, right? However, in most other languages of the same kind, such as MATLAB, R, or Python with NumPy, vectorized code is lower to a C or Fortran call, which is much more efficient than the iterative version for the same languages, which is interpreted. In Julia, the iterative code is not interpreted. It is compiled down to C-like loop. And in the case where you're iterating over an array, which is the typical case, then you don't have to incur any overhead related to the references typically, because it can be stored in an inbox fashion. And furthermore, so in recent Julia, I can even say Julia 1.0 now, union splitting allows to also store arrays in an inbox fashion, even if you have just only a few different types on your array, so a concrete types on your array. So if you have an array of union of only a few concrete types, you can also do that with a little bit of tinkering. Right. This is now the effect of those optimizations on the runtime. Using the same benchmarks, here are the slowdowns compared to Julia with no particular option of other Julias with some optimizations disabled. In green, I disabled LLVM optimizations, so just O0. There is an average slowdown of about 8 times, which is significant, but this is completely negligible with Julia with either inference or devirtualization removed. The slowdowns in those cases are over 100 times slower, which is pretty important. And what's funny is that actually it can be better to remove inference altogether than removing devirtualization, because in the typical case where you have one function with only one method, even if you don't have inference, you can still partially devirtualize it. So you won't be able to devirtualize it down to the specialized method, but you can still devirtualize it to the method, which is, well, good enough. Now, so I said that putting concrete type annotations on your field was important for unboxing. I said that writing type stable code was very important too in order to perform devirtualization and not incur terrible performance. But how is this implemented in practice by packages? We took a selection of the 50 most popular packages on GitHub, according to the number of stars, and under the condition that they passed their own test suites. So we have a very, it is important. So we have quite a lot of those packages, over 7,000 method definitions, almost 800 type definitions. Some packages define only one method, some packages define over 600 of them, and the types are about as variable. Clara is our biggest package. So it is a medium-sized corpus with varying packages style. What we did on them was that we performed a series of static measurements and dynamic measurements that consisted in executing for each of those their test suites and recording for each function call the function, of course, the method that was called, the call signature, and the call site. And we extracted from those measurements a number of metrics. So here are a few of them. This is a very static metric. It's a percentage of typed arguments per method. So some methods have no typed argument. All of their arguments are untyped. Some methods type all of their arguments, and some are in between. So those are taken from the distance package. In the third case, we will say that the method has 33% of all of its arguments typed, right? These are the results. We observe that 82% of methods have all of their arguments typed. So this is pretty important, a pretty big number, and among the rest, it's pretty balanced. So it shows that there is an extensive use of types, obviously, in method definitions, and this is a good thing for packages because if they have to be reusable, they have to somehow allow overloading. And overloading is, I mean, if you want to overload the method, you have to put some type information. Otherwise, you can only overload on the arity. That is a number of arguments. So since Julia allows you to do that, it's better to do it this way. Overloading, so actually, we also had a look at that. And for each package, we categorize the package according to the number of overloaded methods defined in them. And we observe that on average, 30% of methods defined in the packages are overloads of existing functions from elsewhere, typically base. This is this is a big number. It's not that surprising from Julia, but still. And we try to manually categorize the most popular of those most overloaded functions into different categories, and we observe that the most overloaded methods mostly come from math and collection categories. So math is typically plus or multiply, which is pretty intuitive because anyone wants to overload plus or multiply with their own custom type. And collection is for length of size typically, which is very useful for fancy data structures. A more dynamic measurement was the number of specializations per method. So what I did here is I opened the REPL and asked what are the different specializations for length of set, which is one particular method of length. There are 12 of them. So what does this show? Well, of course, a number of them are already precompiled. And maybe some of them were actually executed during the very initialization step of the REPL. So that's why. Some methods have many more specializations. So one example is length of tuple that has over 1,300 specializations after executing the test of light graphs. So of course, those measurements depend a lot on what has been executed just before. Here are the results in general. I think there are two interesting points on this graph. The first is the topmost leftmost point. This point represents the methods that only have one specialization, and they are 46% of all methods in our packages. Those methods are supposedly virtualizable because they only have one specialization. Although this is not a static measurement, so it can't be a proof of that. A second thing is that it also hints at the fact that many of those methods probably have concrete type annotations. Because of course, if you have one method for which all of the arguments have concrete types annotations, it can only have one specialization corresponding to those specific concrete types. Right. The other point I want to mention is actually all the other points. They form a heavy tail. This shows that polymorphism is very much used. There are functions that have over 1,000 specializations, and there are a number of such methods all in the way through. So, of course, it's not surprising because Julia is pretty dynamic, but it also shows that even in packages, in libraries where people want to be very efficient, overloading is a very useful thing to have. A last metric I want to mention here is the number of specialized methods per call site, sorry. So here's an example. I have one call site, which is foo of x. Foo is called with 3 different values, 1, the symbol bar, and the value pi. The 3 values have different types each, and as a consequence, I'll say that this call site is calling 3 different targets, which are the specialization of foo for, respectively, int, symbol, and pi. We measured up to 97 different specializations called for one single call site in the knet package, which is a lot because it means that there are 97 values of different types each that were called at the very same points. And in general, and this is the result on the packages. So each vertical bar is representing one package. And for each package, we distinguished the call sites that were only calling one target from those that were calling 2 or plus. This is log scale. 92% of call sites only call one specialized method. So this is a very strong hint at type stability, of course. It's not proof, again, this is a dynamic measurement, but still, and this is pretty obvious from the figure. We have up to 1,000 different call sites that were only calling, 10,000 that were only calling one particular specialized method. So in conclusion, I want you to remember 3 things that are working together in Julia. First, the design is flexible. It is expressive. It is also compositional. You can write macros to extend the syntax. You can use multiple dispatch to do overloadings. But at the same time, this does not prevent optimizations. And, well, this is obvious because Julia was developed under around 10 years by a bunch of people and not huge teams of thousands of them, and is very efficient. Second thing, the implementation leverages choices from the design. For instance, the specialization cycle is reusing the same mechanism as multiple dispatch and is actually occurring at the same time. Moreover, a lot of costs can be removed from the design choices. For instance, typically multiple dispatch, because generic dispatch is a costly operation, but devirtualization can get rid of it all. And third thing, Julia is using the users in order to get performance. If you want to, I think that this is actually part of the language, that programmers have to collaborate to get performance. You have to write type-stable code. You have to type and annotate your fields. Otherwise, it will work, but it won't be very efficient. And this is the combination and the synergy of these 3 things that really make Julia what it is, which is a fast, dynamic language, which is very easy to use. Thank you for listening. Any question?
Really quick question. The methods that were parameterized, were those concrete in particular, or were some of those, you were counting the numbers that were annotated?
Oh, no, just annotations.
They could be
Any kind of annotation. Yeah.
Because it's still
It is very different from continuing only concrete. Right. This is just to show that types are used. Nothing more. It doesn't hint at specialized methods. Yeah.
So the call site specialization graph, is that call site specialization per method body or per specialized method specialization?
Method body. So these are the dynamic call sites and not the call sites in the source code.
Yeah.
We actually use the internal representation of call sites from Julia to get that.
And that's the number you care about.
One question I've had actually in my mind the last couple of days,
Where are you?
right here, is there a difference in performance cost between, let's take a call site that is, like I'm thinking of 3 different scenarios, right? Type stable, and we're able to inline a function call. That's obviously the cheapest. But then is there just one other case where it's type stable and we don't inline? Is that cheaper than the case where it is type unstable and we have to do dynamic dispatch? Does that make sense?
Right,
so I'm thinking
right.
of 2 different
Actually,
cases.
it does make sense. So, first thing, inlining is allowed by devirtualization, Virtualization is allowed by type stability. And all of those links can break at some point. So for instance, if type inference is not good enough on your function, maybe you won't be able to infer that it's type stable. So that's done. If it is type stable, maybe you won't be able, will you be able to devirtualize it all the time? Yeah, I guess so. But if it is devirtualizable, you won't always inline it because inlining comes at a cost too. It requires more space, and there are a number of heuristics that are used to determine whether a function is inline or not. And these are also the use why there is those at inline and at no inline macros that lets you actually choose if you don't want the compiler to choose for you. And there's also the converse, which is that it is possible to partially devirtualize. So when I was talking about devirtualization, I was talking about devirtualization down to the specialized method. But you can also devirtualize down to the method only. And this is less performant, but it still avoids a lot of cost of generic dispatch. So yeah, there are different levels of optimization, right, just to optimize one call site.
Yeah, got a question about, did you actually distinguish between, on arguments, whether people were using, say, abstract type versus a concrete type, or?
For which metric?
When you were checking how many of the had, I thought you had the
Type
metric-
annotations?
What?
How many of them had type annotations?
Right, but did you distinguish between
No,
type?
I think that was the same question here.
Oh.
But no, we didn't distinguish. We just took annotations in general.
And have you looked at what, whether things are annotated, they usually are in structs, whether they're using actually something that's not concrete, because that's a
Right.
performance issue.
So we also measured. So here is the complexity of the type annotations. I wasn't sure if I had time to show that. So it's not. I'm not sure if that's exactly answering your question, but still,
Yeah.
is it related to the data point? So we measured so it's not the same. We're not measuring how much is it typed, but for each of those methods that has a type annotation, how are the type annotations? So are there only where? Are there wheres and unions? Are there bounds on the where? And these are the results. So you can show, it shows that on average there's around 10% of non-trivially, or maybe less, maybe 6% of non-trivially bounded where annotations across packages, which is, well. Good.
Yeah, if you go to this slide where you had the loop that was type unstable, if you remember, you had R and N, and you had a union of the types there. Yeah, so here you should still be able to do some inlining, right? If you split the union and you inline.
Right.
I don't think you mentioned that, did you?
No, I didn't mention that. That's
Maybe
right.
you can
So in Julia
comment on that.
1.0, actually, this will still get optimized thanks to union splitting. That's true. I just wanted to have a simple example, but that's correct. This will still get optimized in the sense that so there will be a type check that's checking whether n is actually an int or a float, and in these two separate cases, it will be devirtualized. So there won't be generic dispatch in that case, but there used to be. Yes.
Sorry, one last question.
Did you check for implementation of fake methods? Like, well, lots of packages, you mentioned like graph, for example, define a method for a function, but just to define the function, and people are supposed to overload it. So it's a fake implementation that's never supposed to be hit. Did you see that in some analysis?
No, we didn't check for those because I wasn't really aware of that, because that sounds like somehow different from the general philosophy of Julia, because there is no basic there is no interface in Julia, and this is an interface. So no, we didn't check for those, but it would be interesting.
Then other people define the function with function f end to have a function defined without any method. Did you see some of these? Well, like function, a name of a function, and no parentheses, just end directly.
Oh, that's just a function with no method, right? Yeah, there are a number of them. I don't know. I don't think we measured those actually.
All right, let's take time, okay?